Hello and welcome back, future scientists. I'm Mr. K with Mississippi Public Broadcasting, and we're going to continue talking about dissecting the science portion of the ACT today. So we've gone through a lot of lessons already. What I really wanted to focus on today is graphs. I'm going to walk you through a couple of steps that you should do every time you see a graph on the ACT. These are a couple of steps that you might want to do, and that's going to increase your speed and therefore increase your score. So thank you so much for being here today. Let's go ahead and get the ball rolling and see what we're talking about. So again, what we're doing today is we're going to look at some graphs on the ACT. These are graphs right off the ACT. I'm going to give you as little information as possible, as little background information as possible, and then we'll look at some of the questions that go with these graphs. Again, these are graphs and questions off the ACT, and we'll see if we can answer the questions by just using the graph. We won't really read all the background information on it. So here's a graph. To the right, this graph is tracking the preference of cockroaches' selection in food. Here are some things that we should quickly identify. Every time you get to a graph, you want to try to identify these key things. So first of all, let's look at the y-axis. The y-axis, this is the one that's running up and down on the left over there, and this is mass, and this is talking about how much food is remaining. Okay, so the y-axis is tracking the food remaining in milligrams. On the x-axis, this is the one on the bottom, okay? This is time in hours, okay? So the x-axis is tracking time, okay? There are many graphs, there are many bars in this graph, and that means that we're tracking several different variables. So you can see at 0 hours, at 4 hours, 16, each of those different numbers, variables on the x-axis, there's 4 bars that we're tracking. Well, make sure to note the key. The key over there above the graph is telling you what the bars represent. So each bar represents a different type of food, okay? There is a strong inverse relationship between the two variables. So as the amount of time increases, the amount of food remaining decreases. So there's an inverse relationship. So what that tells us is that the longer the food's out, the more food is eaten by these cockroaches, okay? The more time passes, the less food remains. That makes sense with what we know about consuming food, right? None of these bars should ever increase because the food's not multiplying. They can stay the same, but if you look carefully, you'll see that at every time interval, they are decreasing, and that makes sense. The cockroaches find the food and they eat a little bit, and so there's less remaining from one time to the next, okay? Here are a couple things that we should be able to point out very quickly. The cockroaches do seem to have a preference in food, right? We can tell that they are eating a lot more of the peanuts, and we can tell that they are not eating much of the cat food. And so, in my experience, just doing so many of these ACT questions, we're going to get questions about the cockroaches' preference in food. You're probably going to get a question that asks, what food did the cockroaches like the most, and what type of food did the cockroaches least like? They might not be worded just like that, but as we go through the questions, that's going to pop up some way. We should be able to see this strong inverse relationship as time increases, the food's going down. So let's look at some of the questions that go along with this graph and see if we can answer some of those questions. So here's the first one. It says, according to figure 1, the mass of cheese remaining at 4 hours was closest to which of the following? Now, I'm not going to put the answer choices up here, but our main goal is just to see, just based off of this question. We have not read, there were a couple of paragraphs that describing what's happening in this graph. We didn't read any of those, but just by going straight to the question, we can find the answer. It's telling us where to look. It tells us to look in this graph, and then it gives us the values. It says how much cheese was remaining in 4 hours. So what we would do is go to the 4-hour interval there, find the bar for cheese, and we can track it right there. It's right over 180 milligrams, right? So we didn't have to do all that background reading. By going to the questions first, we're still able to answer the question. So here's the next question. Suppose a company wants to use food as bait in a trap designed to capture female B. germansenia. Okay, those are the cockroaches that are eating this food. Based on figure 1, which of the 4 foods should the company place in the trap to maximize the chance of catching these cockroaches? Well, this is the question that's asking you, which food did they prefer? They didn't ask it like that, but if you're making a trap and you want to catch as many cockroaches as possible, you want to use the trap, you want to use the food that they're eating the most of. They're eating more peanuts than anything else, so if you're making a trap to catch these cockroaches, you should use peanuts as the bait, right? So that's what that question is asking us there. Okay, let's go to the next one. Number 3 says, consider the statement. The B. germansenia ate the food between 0 and 4 hours, between 4 and 16 hours, between 16 and 24 hours, and between 24 and 28 hours. This statement is consistent with the data in figure 1 for how many of the 4 foods. Okay, well, we should be able to see here, and we did it on that previous slide, that there is an inverse relationship. As time increases, the amount of food decreases. At every interval, these bars are becoming smaller and smaller. So it's all of them. We know that just based off of the trend here. Now, you could take the time and check each individual bar, but that's wasting too much time. Remember, you really want to spend less than a minute per question. You don't have enough time to check each individual bar. We can see by a quick judgment that as the time increases, all the variables are going down. All of these bars are going down. So the answer is all of them. All of them decrease at each of these different intervals, okay? Don't take the time and really scrutinize them that much. If you see a trend there that's very obvious, just pick the best answer and move on, okay? This is going to save you some time. Okay, here's one more question we can answer based off of this graph without even reading the context of what's really going on here. All right, so here's the last question. Question 4 reads, a student predicted that B. germansenia would eat less cat food than ham by the end of the study. Do the data in figure 1 support this prediction? So yes, we know that they're eating less cat food than anything else. The cat food, the bar that represents the cat food are these black bars. You can see that at each interval, the black bar decreases the least. And so that means that the cockroaches don't really like this cat food very much. They're eating a lot of the ham. The ham is the second most eaten object after the peanuts. The ham is the gray bar, and you can see that at the end of the study, there was about 110 milligrams of ham left, and there was almost 180 milligrams of the cat food left. So do the data in figure 1 support this prediction? It does support the prediction. There was less cat food eaten than ham. Okay, so again, we'll do a couple more of these. The whole purpose here is to show you that you don't have to read every single paragraph on the science portion of the ACT. My preferred way to do them when I'm trying to answer these quickly is I go to the questions first. Usually the questions tell you where to look, and that's going to save you some time. Then you only have to go back and read what you need to get the context that you need. Okay, so let's look at the next graph and see if we can kind of break it down in a similar way. All right, so this time we're working with line graphs. Okay, there are 2 graphs over here on the right, so that's going to make it a little bit trickier. It says the graphs to the right track the amount of gas collected under different circumstances. Experiment 1 is testing 3 elements at different masses to see how much gas is produced. Experiment 2 is testing 3 different elements at different temperatures to see how much gas is collected. So again, I did not read the whole background on these passages. I just looked at the graphs, and just by looking at the graphs, this is what I'm able to figure out. Okay, let me walk you through the steps of some things we should quickly be able to identify, and that's going to help us get to that conclusion as well. Okay, so let's look at the y-axis on both of these experiments. Okay, the y-axis for experiment 1 is volume of gas collected in milliliters. The y-axis for experiment 2 is also volume of gas collected in milliliters. So that means that the y-axis on both of these is the same. Let's look at the x-axis for experiment 1. This is talking about mass, and the units that we're using here is grams. On experiment 2, the x-axis is temperature. Okay, so what does that tell us? The y-axes are the same, and the x-axis are different. So what we're really trying to figure out here is something to do with gas collected. How much gas are we making under these different circumstances? The top graph is going to test different masses, and the second experiment is going to test different temperatures. But the elements that we're using is the same. If you look at the key up there, the three elements that we're using in both of these are the same. It's iron, nickel, and zinc. Okay? Experiment 1 has a direct correlation. The greater the mass, the more gas is produced. So look at that top graph over there. You see how it's an upward slope? This is a direct correlation. So what's going on here is that as the mass increases, the amount of gas collected also increases. Let's look at experiment 2. Experiment 2 also has a direct correlation. The higher the temperature, the more gas is produced. Okay? Here are some other things that we can quickly identify. Fe, or iron, that's what Fe stands for, is iron, produces the most gas in both studies. Okay? Iron for both of these is the line with the circles on it, and you can see on both graphs that line is the highest. Okay? And then zinc, or the Zn, produces the least amount of gas in both studies. So I would not be surprised if we get questions about that, talking about which is making the most or which is making the least. Some other things that we want to note, because these two graphs are so similar, and the only thing that's different about them is the x-axis, we're probably going to get questions to compare these two because they're so similar. They're going to ask us about why are they so similar to each other. You're going to get questions that has you comparing the two graphs here. Okay, so let's look at some of the questions and see if we can identify the correct way to approach these. All right, so number 1 says, consider the volume of gas collected in the trial in experiment 2 for nickel at 30 degrees Celsius. The same approximate volume of gas was collected in trial 1 in experiment 1 for what mass of nickel? Okay, so it's telling us where to look. The first sentence says, consider the volume. So what does that mean? It means go find that. And so what we'll do is we'll look at figure 2. It's telling us nickel. Nickel is the line with the squares at 30 degrees Celsius. So I can find that. It's right here. You can see it's right under 130 milliliters. Okay, so I know I'm going to have to use that and find that value somewhere on table 1. So it says the same approximate volume of gas was collected in the trial in experiment 1 for what mass of nickel. So we're going to try to find where 130 milliliters of gas was collected for nickel in experiment 1 and try to figure out what the mass was for that one. Okay, so I'm going to come up here to figure 1 just like the question tells me to. I know I'm looking for about 130 milliliters, so I'm just going to go over until it gets pretty close to the nickel, and I can see right here at 0.3 grams, I've created the same amount of gas here as I did with the first sentence there. So that would be my answer, is about 0.3 grams. Okay, great. So let's look at the next question here. Number 2 says, how many temperatures were tested in experiment 1 and how many temperatures were tested in experiment 2? So again, it's having us compare the two different experiments here. Okay, look at the one sentence above Table 1, Figure 1, look above that. It says, in each trial, a selected mass of iron, nickel, or zinc was tested at 30 degrees Celsius. So there was only one temperature tested in the top figure, right? Because it tells us they're all tested at 30 degrees Celsius. So we're getting one temperature from Figure 1. Let's see if we can figure out how many temperatures were used in Figure 2. So this one says, I'll read that brief one sentence above the experiment again. It says, in each trial, 0.3 grams of iron, nickel, and zinc was tested at selected temperatures. Okay, so let's look at Figure 2. I see a lot of different temperatures down here. I see 10 through 50. Okay, well, does that mean that 40 temperatures were tested? No, because we actually don't have any points plotted for all of those. Let's look at Figure 2 and just count the amount of trials that you're seeing. I see points plotted above 10. I see points plotted above 20, I see points plotted above 30, I see points plotted above 40 and 50. So those were the only temperatures that were tested because that's the only thing that we have data for. If there were points plotted at different temperatures, then we could, there would be a different amount tested here. But we're getting one temperature tested from up here, and then 2, 3, 4, 5, and 6. So 6 temperatures were tested in all, 1 temperature from the first one, and then 5 from the bottom one. And again, I'm just counting where those points are being plotted there on figure 2. Great. So let's go to the third question and see if we can figure this out. This says, which of the following statements describes a difference between experiments 1 and experiments 2? So what are some differences here? What we want to go with is that in experiment 1, we used different masses, but it was 1 temperature. And then in figure 2, there was 1 mass, but different temperatures. So that's the main difference here. They're still trying to figure out how much gas we're collecting. The main difference is how are we getting those different values. In the top, we're using different masses, and in the figure 2, we're using different temperatures. So that's the main difference in between these two. So again, if you get questions where the graphs are very, very similar, you can be expected that you'll have to compare and contrast them at some point. Okay, so here's question 4. If a temperature of 5 degrees Celsius had been tested in experiment 2, would the volume of gas collected for zinc more likely have been greater than 107 milliliters or less than 107 milliliters? Okay, so this one's a little tricky, but let me give you a hint here, okay? This sentence is a key phrase here. It said, if a temperature of 5 degrees Celsius had been tested. That means that it was not tested. It's like saying, imagine, or what if we did this thing, right? And so that's telling me that I'm not going to be able to find this point on this graph anywhere. This is something called extrapolation. What I'm going to have to do is find that information in the graph and then project it beyond the range of the graph to find my answer. Okay, so what are we looking at here? We're testing zinc. So let's try to find zinc at as close to 5 degrees Celsius as possible. Okay, so zinc is the triangles. So I'm looking at figure 2. It tells me to look in figure 2 in the question. So I'm looking at figure 2. I find zinc. It's the line with the triangles. And I see that the closest I can get to 5 degrees Celsius is 10 degrees Celsius. Okay, well, at 10 degrees Celsius, zinc produced about 107 milliliters of gas. And so my job here is to project this graph, the trend of this line beyond the graph. Okay, well, if I were to go to 5 degrees Celsius, which is a little to the left, do I think my line would go up or down? Well, just using the angle of the graph that I have, I would assume that it would go down. Now, I don't know because I didn't do this experiment. I'm really taking an educated guess here, right? But when you get a question like this, they're not going to change the trend up. I can see here that this trend is the farther left I go, the smaller the value is. The farther to the right I go, the higher the value is. So when you get a question like this, you can assume that the trend is going to remain the same and that we're not going to get some odd phenomenon that doesn't fit with the rest of the graph. So what I'm seeing here is that this line, as I move from right to left like this, the value's getting smaller and smaller and smaller. At 10 degrees Celsius, I produced about 107 milliliters. So if I were to go down to the left a little bit more at 5 degrees Celsius, do I think that value would be less or greater than 107? It would be less than. Based off of the trend that of the graph that we have available, the answer would be less than 107 because 5 degrees Celsius is less than 10 degrees Celsius. So that's kind of how you want to think of these. If you have to extrapolate or interpolate when you're putting information into the graph, the trend is mostly going to stay the same. They're not going to change it up because how would you be able to answer that question, right? Okay, great. I think I got one more for these graphs and then we'll move on. So 5 says, suppose that the trial in experiment 1 with 0.25 grams of zinc is repeated, except that the inverted graduated cylinder is replaced by an inverted test tube. each filled with 60 milliliters of water. Based on figure 1, how many test tubes will be needed to collect all the gas? Okay, so what's going on here? First of all, like I said, we did not read the background information on this, how this experiment was conducted. For these questions, we didn't really need to read it because most of the information is right on the graph. There's a bit here that we're not getting. So it's saying, suppose that we did the trial the exact same way, except the inverted graduated cylinder is replaced by inverted test tubes. So obviously they are using graduated cylinders here. We just didn't know that because we didn't read the explanation of the experiment. You still don't really need to, because what it's asking is, so let's replace that graduated cylinder with test tubes. And each test tube can hold 60 milliliters of water. How many test tubes will we need? What this is saying is, can we find this value that they're giving us and then figure out how many test tubes we're going to need? So that's where we're going to start. It says experiment 1, so we know we're looking up here, and it's saying 0.25 grams of zinc. So let's see if we can find that value. So I'm looking in figure 1, I'm looking for zinc, that's the triangles, and one of the variables on the x-axis is 0.25 grams. So I can see at 0.25 grams of zinc, right over 90, maybe 95 milliliters of gas were created. So how many test tubes am I going to need? Well, I'm going to need more than one because each test tube only holds 60 milliliters, so I'll need 2. Right? Because if I had 2 test tubes, that would be 120, and this 95 is less than 120. So I would need 2 test tubes instead of that graduated cylinder. Again, for these questions, these were most of the questions for this passage. We didn't really read the paragraph that was explaining the experiment. We didn't need to. You can read it if you want to, but if you're trying to increase your score, we have to manage our time. And one way you can manage the time is by don't do any reading that you don't have to. And so again, when I approach these questions, I go to the questions first, see if they give me enough information to answer them, and then if I don't feel like I know what's going on, then I go back and read the explanation of what's happening. But for these 5 questions, you maybe would have gotten 1 or 2 more. For these 5 at least, we didn't have to read the explanation. Just looking at the graphs were enough. So as you practice doing these ACT questions, that might be something you want to consider. Okay? So here's our last little practice graph. Okay? So let's look at this one. This is another line graph. Line graphs and bar graphs are the most common graphs you'll see on the ACT, so these are good practice. This says these graphs to the right track the change in electrical currents over a 20 millisecond time interval. Here are some things that you should identify quickly when you get a graph. You always want to look at the variables first, or the axes first, sorry. So I'm going to look at the y-axis. For the y-axis on figure 2, kind of confusingly, there's actually 2 variables. So you can see on the left-hand side of figure 2, it's talking about amperes, which is A, and then on the right-hand side of figure 2, it's talking about voltage, which is V. So this one actually has 2 different variables on the y-axis. Okay, and then on the y-axis for figure 3, it's voltage. So figure 2 and figure 3 do share a y-axis variable. They're both tracking voltage some way. Okay, let's look at the x-axis for both of these. So the x-axis for figure 2 is time in milliseconds, and the x-axis for figure 3 is also time in milliseconds. So these graphs are very, very similar. On the x-axis, they're both time. On the y-axis, they're both voltage. So they're very, very similar. So in my educated understanding of this, we're probably going to get questions where we have to combine information from these 2 graphs. Because they're so similar, they're going to almost treat them like they're the same graph, because what's on figure 3 could be graphed on figure 2. We could kind of overlay them and the information would still line up. Okay, so the x-axis are the same and the y-axis both track voltage on both of these figures, but figure 2 is also tracking a different variable, amperes, but that's only for the I line, the solid line there. Okay, the change between I and VS in figure 2 are very similar. So look at figure 2, you see the solid line and the dotted line, they're perfect matches for each other. They're just offset a little bit, but you can see how they increase a lot for the first couple of seconds, and then there's a long decrease in the middle, and then they both start to increase again. So they're very, very similar. Okay, and then the changes in figure 3 are different. So when I look at figure 3, those 3 different lines don't have the same mirror image quality that figure 2 has. They're all they're not perfect matches like those are. So that's just something we kind of want to note here, okay? So let's go ahead and look at the questions and see if we can start answering these. Again, this is figure 2 and figure 3. So that means that this question had a figure 1, but it's not on here. We just have figure 2 and figure 3. So we did not read the background explanation of the experiment. We're not looking at figure 1. Let's see if we can answer the questions just by looking at these 2 graphs here. Okay? So number 1 says, according to figure 2, the maximum positive value for VS was approximately. Okay, so what do I want to do here? Well, it's telling me where to look, right? I don't really need any background information. The question tells me exactly where to look. It says, according to figure 2, so I'm looking here. The maximum positive value for VS was what? Okay, well, something you do need to know is we have to look at the key. The key here is telling us that VS is the dotted line. So all I have to do is find where that value was the highest. And you can see up here at about 0.25 voltage, that's the highest that it goes, right? This is the crest of the wave, and so that's the maximum value for it. Okay, let's look at question 2. So 2 says, a period is the time required for a wave to complete one full cycle. Based on figure 3, the period for VL was. Okay, great. So this is telling us where to look again. It says in figure 3, so this is the bottom right corner, and we're looking at VL. Okay, that's the dashed line, not the small lines, but the slightly longer lines. Okay, so that's the line that we're looking at there, and it wants to know what a period is. Okay, this one you do need a little bit of background information. It does tell you that a period is the time required for a wave to complete one full cycle. Well, what does one full cycle mean? One full cycle means either from crest to crest or from trough to trough. Let's look at this line here and see if we can identify anything. So looking at this line right here, okay, I see a trough at about 10 milliseconds. That's the lowest that it goes. But there's only one trough here, and so I don't have enough information to base it off of that. Okay, but you can also go from crest to crest, and crests are like the top of the wave. So can we find 2 tops of the wave? Well, here at 0 milliseconds, that's about the highest that wave is going. And then over here at 20, that's another crest. At 20 milliseconds, that's another crest. That's as high up as the line is going. So how long does it take for one full period to happen, one full cycle to happen? Well, it's 20 milliseconds. From 0 to 20 milliseconds, that's as long as it takes to start at a crest, go all the way to a trough, and then to hit the other crest at the end of the graph over there. Okay, great. So let's keep it going. Number 3 says, according to figure 2 and 3, which voltage varied the least during the 20 millisecond interval? So it's asking us to look at both variables, and it wants to know where the voltage varied the least. Okay, well, if we're looking at where the voltage is varying the least, that means we want the line that has the smallest difference in between the crest and the trough. So the highest point and the lowest point, the ones that those are the closest together is going to be where the voltage varied the least. Okay, so it tells us to look at both figures. So let's look at figure 2 first. We're looking at this VS. The smallest the line got was at about 18 milliseconds. That's maybe 150 voltage. And then the highest was 250. So that's almost a 300 voltage difference in between the crest and the trough. Okay, so not feeling confident that that's our answer, but let's check the other ones too. All right, so I got VR at the top for figure 3. VR is the solid line. So let's again find a crest and a trough. The crest for VR is about 150 voltage, and then the trough on the right, closer to 15 milliseconds, is about negative 150. So that's almost a 300 voltage difference as well. Let's look at VL. VL was the one we were looking at for the previous question. Okay, so the highest, the crest for VL looks like it's at 50 voltage, right? It's right over the zero. Okay, and then the lowest it goes, the crest, or sorry, the trough is about negative 50. So that means that there's just a difference of 100 voltage here. And then you can look at VC, that the crest and the trough for VC is widely higher. You can see that it's varying a lot. So our answer here is going to be VL, just because the crest and the trough are basically the closest together out of those different variables that we looked at. Okay, here's the last one. So 4 says polarity refers to whether a voltage is positive or negative. A voltage of 0 voltage has no polarity and can be ignored. Based on figures 2 and 3, which two voltages were always opposite in polarity? Okay, so we're going to have to check all of these different lines, and we want to see when their polarity was the opposite. So what we're really checking here is when one line is positive, the other line needs to be negative, and vice versa. If we can find that, that's going to be our answer. So let's check VS first. Okay, so VS starts off negative, and then it gets positive for this part from about 3 milliseconds to 13 milliseconds. So there's 10 milliseconds where it's positive, and then it gets negative again over here. Okay, so looking at my answer choice, looking at comparing them to figure 3, there's no line that's going to match that one or be the inverse of it. Okay, two lines that are looking really good to me right off the bat. Let's compare VL and VC. So you can see that VL, this is the longer dashed line, starts off positive, and then at about 5 seconds it switches polarity and is now negative. Compare that to VC, it's the exact opposite. You see how VC and VL are meeting? They're overlapping at 5 milliseconds and at 15 milliseconds. When one is negative, the other one is positive, and vice versa. Okay, so those are going to be that's the correct answer, is VL and VC. When VL is positive, VC is negative, and then they switch, they're at about 5 milliseconds. Okay, so that's going to be the correct answer for that one. So y'all, thank you so much for making it today. Hopefully walking through those graphs with y'all is going to help increase your time and increase your score on the science portion of the ACT. Your teacher has some other work for you to do, so make sure to give that your best effort, and I hope everybody has a great day.